Okay, the law of combining volumes. Now we want to get back to chemical reactions. Up to this point in the gases unit, we essentially, number one, learned about the physics of gases. That got us Boyle's law, Charles' law, the combined gas law. We then defined the ideal gas law, PV equals nRT. And that gave us a way to calculate moles from the volume of a gas, which brings us back in line to what chemists want to do. Now we've used the ideal gas law to put together some molar volumes, some useful conversion factors to convert liters into moles and moles into liters. And that's really just talking about individual gases on their own. We haven't been dealing with any chemical reactions. None of our problems have stated reacts with, is combusted, etc., etc. Now we're going to get back into the chemical reactions. The law of combining volumes is one of those chemistry laws that was actually discovered, probably one of the first chemistry laws. We've heard of some chemistry laws throughout this course. We've learned about the law of conservation of mass. Chemical reaction takes place, mass is the same before and after. That was Lavoisier, with his scales. We've talked about the law of constant composition. Water, if you break it apart, you get 11% hydrogen, 89% oxygen, and you can take that water from, the Sydenham River. Not that I'd want to get too close to Sydenham River, but anyway. Nobody here from Almaden? Nobody's offended about the Sydenham River? Anyway, okay. Or you could get that water from Lake Huron, and that water would have the same composition. It defines what water is. The law of combining volumes was probably one of the first because chemists were decomposing substances into their individual elements, and many of these substances they were decomposing contained the gases, nitrogen, oxygen, hydrogen, all that type of thing. They were using electricity to decompose them. And when they decomposed them, they obtained a certain amount of gas. And then when they started working with the gases, they tried to react them back together. Some of them produced a gas as a product, all right? An example of a reaction that was done would have been to take some hydrogen gas and react it with some chlorine gas to produce some hydrogen chloride gas, all right? Now to balance this up, we've got 2 and 2, and we need a 2 there, so it would look like that. And when chemists did that, they realized that the volumes of the gases that they used always combined in a certain way, hence the law of combining volumes. They didn't combine differently each time. They were coming together, or they were separating out in a particular certain ratio. Don't write this next slide down. It just contains some information. But we'll work on a problem here in a moment to illustrate it. This is a reaction that Joseph Gay-Lussac, he's the one that did the pressure-volume pressure-temperature relationship. Anyway, he discovered that when you took 1 liter of the chlorine gas and you reacted it with 1 liter of hydrogen, you ended up with 2 liters of hydrogen chloride every time. Now you might think that is truly combining volumes because 1 liter plus 1 liter makes 2 liters. But if we go back and take a look at that original slide where I've got it written down, you'll notice that we've also got a 1:2 ratio, all right? So it actually works out that this law of combining volumes isn't just adding volumes, but it comes from the mole ratio. Now they knew nothing about that. They just realized, hey, this is neat. We always get this neat ratio out when we deal with gases and we're doing the chemical reactions. Let's do a little example just to show why they were getting the result that they were getting. You can write this down. Let's say that we're actually doing the calculation to calculate this reaction that he was observing. We're going to use stoichiometry to calculate it. He knew nothing about stoichiometry at the time. The atomic theory hadn't been discovered. This was actually probably before Lavoisier, so he hadn't even talked about conservation of mass yet. Now I've given you a pressure of STP just to make the question nice that we don't have to do too much calculations. And again, since this is kind of a reminder of what we do when we do stoichiometry, right? We're kind of reviewing. You'll notice it says reacts with. That's one of your words that's going to give you a cue. Hey, I've got to do stoichiometry here. What's the first thing I need? All stoichiometry problems, the first thing I write down is balanced chemical equation. I did that on the first slide. I'll rewrite it here. I'm going to make sure I'm on the right slide thing because I don't like the way this thing, I'm backing up. Okay, so H2 plus Cl2 to produce HCl. They're all gases, 1, 1, 2. As I normally would, I would write the information that I have underneath each of the things. And in this case, we've got volumes of gases. I've got 1.0 liters and 1.0 liters. And I want to figure out how much HCl is expected. Well, unfortunately, our nice little simple example isn't so nice because notice I've got both numbers for the reactants, which makes it this type of problem. What type of a problem have I got here? Yep, Esther? Limiting reagent problem. So I'm going to have to figure out how much Cl is needed, and then we're going to figure out which is limiting, and then we're going to go ahead and do that. All right, that's not a big deal. So I'm going to head down here from liters down to moles, but this is liters of a gas, and it is at STP. So what's my conversion factor to convert liters to moles at STP? Yes? Yeah, molar volume. I'm going to use the molar volume at STP. I'm not going to write that in because we'll get that in a moment. I'm going to head over here to moles, and then I'm going to move back up. And so now I'm going to have moles of Cl, and I'm going to move back up to Cl2. And how do I convert my moles back into a volume? Still at STP. Yep. Molar volume. Well, let's go ahead and do that. Writing down what I have first, 1.0 liters of H2. I guess I haven't been putting the H2 in, but we'll put it in this time. I'm using the molar volume at STP, and I want to get rid of liters, 22.4 liters per 1 mole. And now I need my mole ratio, what I have on the bottom, what I want on the top. And now I put in my molar volume, still at STP, and this time I need to get liters out. So it's on the top, and 1 mole's on the bottom. And yes, Nick had his hand up, and I told him. Now, let's take a close look at this calculation. I don't believe we need to get any calculators out at this point, because what do you notice? What do you notice? Yep, Amber? Sorry? Right. The 2 molar volumes cancel out, except for the 1 liter, and I guess 1 over 1 cancels out, right? But you're right. The 2 molar volumes cancel out. This gets rid of this. Now, the reason they cancel out is because my 2 gases that I'm interested in are both at the same temperature and pressure. And remember, I've been talking about how the fact that it doesn't matter what the identity of the gas is, as long as it's at the same temperature and pressure, they will have the same number of moles. This is why the law of combining volumes works. Because every time you do the problem, if it's at the same temperature pressure, whether it's STP or SATP or any other temperature and pressure, if I had to use PV equals nRT, I would have had to use it twice, and they would have been the inverse of each other. For any time that I have a chemical reaction that has more than 1 gas, and it's at the same temperature and pressure, I don't need these conversion factors. It's as if I can take a shortcut and go straight across. And the only conversion factor that I need, well, what's the only conversion factor that's left in the whole thing? Yep. The mole ratio. All I need is the mole ratio. That's the shortcut of the law of combining volumes. Because the volume directly tells us the moles, I don't really need to go to moles because that ratio is going to do it for me. So what have we got? We've got 1.0 liters here, which means nothing's limiting. They're the same. I can choose whichever one. But now I can take the shortcut. I can go straight across to there and get my volume of my gas straight with the mole ratio. So to find the answer, I can put my 1.0 liters. I can start with H2. It doesn't matter which one. Now, I'm not even going to worry about molar volumes anymore. I'm going to just use the mole ratio. What I have on the bottom, what I want on the top, and I'm going to end up with 2.0 liters. All right? That's the law of combining volumes right there. That it's the mole ratio that determines straight up how much volume of a gas you have. So what were they looking at? What were Mr. Gay-Lussac, what was he seeing when he was seeing the law of combining volumes? He was actually seeing the mole ratio. But they knew nothing about atoms. They knew nothing about molecules. They knew nothing about moles. But that's what they were looking at, the mole ratio itself. All right, let's do a couple of example problems now that we know this shortcut. And then I'll give you some work, and I'll let you work from there. So you can write that down. That's the law of combining volumes. Don't write down this bottom part. We already just wrote this down. We just wrote that down in our example. It's just saying that we can look at that mole ratio in terms of moles, or in milliliters, or liters, or any volume unit. As you are writing that down, I've got a little extra worksheet with some practice problems. There's also a little bit of textbook work. When measured at the same temperature and pressure, the volumes of gaseous reactants and products of a chemical reaction are always in simple whole number ratios. Well, it's a simple whole number ratio because it's the mole ratio. The people who created the law of combining volumes didn't know about a mole ratio, but now to us it's quite clear. So if you've got a problem and it's going from a gas to a gas and they say it's at the same temperature and pressure, or they give you numbers and they're the same, you can ignore the numbers and just use the mole ratio. Why is this true? I do want you to write it down. This is a little historical bit of information. There actually was a scientist by the name of Avogadro. He looked at this law of combining volumes and wondered why this was true. Now, he wouldn't have used the term molecules because the term molecules wouldn't have existed. But he did realize that there had to be particles, pieces to it. And he has essentially said equal volumes of any gas at the same temperature and pressure contain the same number of molecules, same number of particles, entities. We can see that with PV equals nRT. If it's the same pressure, then pressure is a constant. Not that it's gone, but it's just a number. And if it's at the same temperature, then the temperature is constant. And R, well, it is a constant. And that means volume is directly related to the number of moles. And so if it has the same pressure and temperature, then that volume will have the same number of moles, even if we're talking about two separate gases. It was Avogadro's hypothesis, along with the ideal gas law and some other calculations, that allowed chemists to calculate Avogadro's number, 6.02 times 10 to the 23, which is why they call it Avogadro's number. It was based on his original idea. Okay, now this is the example. I'll put that up in a moment. All right. You don't know what butane is. I will give you that information if I'm asking you a question like this. This is a combustion reaction. Butane is the fuel, right, found in a lighter. And so we're combusting it. 120 milliliters of the butane. We had about, 90-some milliliters of butane. We didn't combust it the other day. Butane, though, I did put the formula on the board last time. It is C4H10. And we are combusting it. And goodness gracious, I'm hoping we know what the products of combustion of a hydrocarbon are by now. What are we going to get when we burn it, Ben? CO2 plus H2O. And let's balance it. 4. We've also done this a million times. 10, which means we need 5 H2Os. That's going to give us an odd number. That's okay. We can use a 0.5. The CO2 contains 4 O2s. If I divide 5 by 2 to create O2s, that's 2.5. 2.5 plus 4 is 6.5. Now you might say double that up, and if I were testing you on the proper way to balance a chemical reaction, by all means double it up. But if I'm just doing stoichiometry, I'm just going to create a mole ratio out of this, and 1, to 6.5 is the same as 2 to 13. Mathematically, it's the same. So don't worry about doubling up when you're doing a stoichiometry problem. Again, let's write our information underneath. I have 120 milliliters of butane, and in part A, I want to know how much oxygen is needed, and I don't need to go all the way around through moles. I can go straight over there with a mole ratio, and then I'm done the question. Doesn't even have to be in liters. Gas to gas stoichiometry at the same temperature and pressure is the easiest. 120 milliliters, what I have on the bottom what I want it to become on the top. Yep. You've got an extra 0 in there somewhere. $780 milliliters. That's it. It's that simple. Part B, I'm wanting to know how much carbon dioxide, so I'm heading over to there. Same thing, mole ratio. Again, 120 milliliters. What I have on the bottom, what I want on the top. I can handle this one. 480. Pretty good, eh? 480 milliliters. That is the law of combining volumes. Oh, did it all disappear? Is it ever going to come back? It's never going to come back. The answer was 480. All right, there's a few questions in the textbook, and you've got the worksheet. And I will let you work for the rest.